Good afternoon. There's all excitement here today, huh? About the midterm. Can you calm down a little bit? Then you can concentrate even more on the midterm later. Hello out there. Good afternoon. Can I have it a little louder, please? Obviously. They all shook up from the earthquake here, isn't that right? Okay. So the midterm will be 40 questions. You will have 2 hours. It will be all multiple choice. Everything that we have discussed until Friday, from the day after the first midterm to Friday, will be part of this. And if you had to read something, that will be maybe part of it too. Okay? Today we're going to continue talking about gases. And you have seen that P times V is a constant. Pressure times volume is a constant. And we are interested in how we get to this constant. We want to investigate the microscopic origin of pressure and temperature. So pressure and volume and temperature, these are macroscopic entities. So how do we get microscopically to pressure and temperature relation of gases? And you remember when we had these balloons, that we sort of had this picture that these particles, the gases, that they are exerting momentum on the walls, banging against the walls, and keeping the balloon inflated. So this pressure neutralizes the outside pressure. With this, we have some kind of an inkling that it must have to do something with momentum transfer. So let's talk about a little bit more about the kinetic theory of gases. And so if you have momentum transfer, for example, this is your wall here, and so if the pressure has to do with momentum transfer, and momentum is m times v, that means that it hits the wall and then it gets bounced back on the wall, and then it transferred momentum here. And if you have, for example, a boxing glove, where you have, for example, I have a very small hand, so it has not much mass. In order to transfer a lot of momentum, I have to hit it very hard, okay? All right? And if you have this huge guy, he has a hand about 5 times as big as mine, he just does like this, boom, there you go. So mass times velocity is momentum. So he has a lot more mass, he needs less velocity. Same kinetic energy, though, that is delivered, okay? So let's look at this, for example. If you are standing there at a party or something, and there are little kids around, and they have these toys, and the toy car hits your foot. That's something like this. You look at this, there's not a whole lot of momentum transfer there, okay? So it had mass and velocity. The velocity might have been relatively high, but the mass was just very small to really make an impact on you. However, if this would be something like this, if you have a very massive thing like a bus or a truck, it doesn't have to go very far. If this thing hits you, there you go, okay? That's a lot of momentum transfer. And so I would like to walk you a little bit through the kinetic theory of gases today. And there are 4 conditions that we have to agree on when we talk about the kinetic theory of gases. So the gas, an ideal gas, consists of identical, well-separated particles. So there's a lot of nothing in that volume where gas is in there. So if you would compare this to number density of population, California would be not a good example, because there are just a whole lot of people living there in this relatively, no, it's not that small in the state. If you go to Montana, it's also a large state, but hardly anybody lives there. There's very low number density. There's all empty space in between. This is how you can look at a gas. Most of it is empty space, all right? And then these gas particles, or the molecules or atoms, the gas particles, they move in random direction with a distribution of speed. So they have all kinds of speeds, because they have all kinds of sizes, of course, and they have a random direction, so they move in all 3 directions in space, and they have a distribution of speed, as I said. What they do differently compared to people, they move in straight lines. Between each collision with the wall, or if they collide with each other, they move in straight lines. Okay? And then, that's also different from people, when they collide, the particles or the walls, they collide with each other, with particles over the walls, they have elastic collisions. That means there is no loss of kinetic energy, just a transfer of the kinetic energy either to the wall or partially to the other atom. Now, in real life, you have inelastic collisions, because when you collide something with another object, very often there is heat given off, and you lose some of the energy in terms of heat. So this is called the inelastic collision. But these particles, in the ideal gas theory, the kinetic theory of ideal gases, these are elastic collisions, okay? And they move in straight lines. Now, let's do a little bit of heavy lifting here. In terms of some, I gave you I had something handwritten for you, and I would like to go over this now. And at least for some of you, I would like to explain how you get from this macroscopic entity of pressure and temperature, how you derive this from the microscopic picture of this momentum transfer. And so I'm going to do this here on Elmo. Let's see if you can project this. It's not very bright there up there, huh? You cannot read this. So let's see. We're getting better. Can you read it now? Yeah? That's the best way? Everybody can read it? What does it say up there? Of pressure. That's what I just said. Okay. The microscopic origin of pressure. So let's see. We know that a force is a mass times acceleration. Okay. That's force. That's Newton's second law. And so if we think of a particle in a one-dimensional box, so this would be the wall here. This has an area, and that box has the length of L here. Can you see this well up there? Yeah. That's the length of L. So the mass is the change in velocity divided by the change over time. What does this mean? The change in velocity over change over time. So that's essentially what acceleration is. The change in velocity over change over time. That's called acceleration. And so if I look at this here, and I say, okay, this particle has a mass of m, and then the velocity, it has to hit the wall and then comes back out. So one velocity is vx, but it has to come back out. So that's 2vx. That's this here, okay? You're still with me, aren't you? Okay. And then the next thing is, what is the change in time? That's essentially the frequency between that particle when it hits the wall again. So what does that mean? This goes the length of the box. It has to go to the left and then come back up and then hit the wall again. And so it goes back and forth in the box. That is 2L divided by the speed of that, or the velocity of that particle. This gives you now the change in time, or the frequency. How often that particle, this says how often that particle essentially hits that wall. So now we have an equation, F equals m times, the 2 we can cancel here. So we have this we take up here. So we have vx squared divided by L. Vx squared, there it is. Vx squared divided by L. This is for one molecule. So now we want this for a whole bunch of molecules, which we call a mole. And I said that they have an average velocity. One has a specific velocity, but a whole mole, they have an average velocity. Oh, okay. We say v bar in the x direction is the average velocity in the x direction of all particles. And I need to square this divided by L, and I multiply this here by n. And with this, I have the total force for n molecules. Okay. But I don't want any force. I want pressure, don't I? Pressure is force divided by, it says right here, unit area. Okay. So this is my unit area here. No, you can see it now. This is my unit area here, that wall here. And so if I say, I put this in here, n, and m times vx velocity, the average velocity, divided by L, this is this here, and then I multiply this with A, or divided by A, because I have divided by A. I had the force divided by A. So what is the length times the area? That's a volume, is that right? Okay, so I say this is a volume, and with this I say, P times V, I bring this over here, P, thank you very much for telling me. P times V, so I have this here P, and this is V, I bring this over here, P times V is N times M times the square velocity in the x direction. But I'm really not interested only in the x direction, so I say that x direction I express as the velocity of all directions, so this is 1/3 then of the average velocity in all directions, so I just put that 1/3 in here for this here, and with this I get P times V that I have over here is 1/3 times that velocity, the average velocity squared, times the mass, this is I had here. That's now the microscopic origin of P times V. See that? This is the number of moles, that's the type of moles, or the mass, and that's the average velocity. Okay. So now I have a macroscopic observation, pressure times volume. I have explained this with microscopic components. So what is this for a specific gas at a specific temperature? What's the value for this? I don't need a value. Is the value changing? Does the value change, or is this a constant? P times V is what? Who said that? Boyle. Is that right? The guy who did the suffocation experiments? Remember? P times V is a constant. And this is that constant. For each given temperature, for a fixed temperature, a certain mass. Of course, if you have a different gas, this will change that constant. And the temperature velocity will also change because you change the mass. Okay, here's your constant. So that's the first part of heavy lifting, and I hope you have understood part of this. So we just want to see the origin of the temperature now. Okay? So P times V, that's what we just derived, is 1/3 N times M times V bar squared. Okay? There's nothing new, we just did that here. But we also know from our ideal gas law, P times V is N times R times T. So I say, then 1/3 N M V bar squared equals N times R times T. There's nothing wrong with that. That's what I'm going to do here. So this is our microscopic observation, and this is our macroscopic observation. R is the ideal gas constant, N is the number of moles, and T is the temperature. Okay? This is given. I have given you this as a handout if you ever download the handout. So now we're going to rearrange this. So we put the 3 over here. We have 3 nRT. And then we have the V square here, and the NA, that should be an NA here, okay? The NA we put down here. What is NA times N divided by N? What's that? That's right there, isn't it? Okay, that's the molar mass, exactly. So we have V bar squared is 3RT divided by M, okay? 3RT divided by M, now bring that M over here. So I have M times V bar squared is 3RT, is that right? So if I multiply this whole thing on the left and the right with 1/2, what do I get? Then I have 1/2 M times V bar squared. What is that? That's the kinetic energy. And this then 3/2, because I multiplied this with 1/2, I did it here, I need to do it here, is 3/2 RT, and that's the kinetic energy. Now, the kinetic energy, if you look at this now, per mole is independent of your gas at a fixed temperature. You see that here? Kinetic energy is 3/2 RT. That would be per mole. Now I can do this per molecule. The kinetic energy, that's the average kinetic energy then. So I 3/2, and now R, if I divide this by NA, I get a new constant, the Boltzmann constant. R divided by NA is the Boltzmann constant, KB, times T. So this is per molecule, or per atom. Yes. Thank you. So did you see that already, or have you seen anything? So here where we were here, okay. 1/2 mv squared is 3/2 RT, and this is the kinetic energy. So if I look at this here, the kinetic energy is just dependent on the temperature for the gas. Okay, and you will understand later why. 3/2 RT. If I want to do this per molecule, I have to divide this R by N. If I divide R by N, I get a new constant. It's called the Boltzmann constant. And the Boltzmann constant is joule per Kelvin. It's 1.381 times 10 - 23 joule per Kelvin. This is then 3/2 KB times T. This is the kinetic energy. Again, it's independent of the mass. It's just dependent on the temperature. Is that interesting? That's actually beautiful. Maybe for you. Or maybe for me, not for you. Okay, so we have now seen the microscopic origin of pressure and temperature. And let's see what we can do here. I give this to you a little bit more here. And we just did this here. P times V was this here. Okay. So V square is the mean square speed. We called it mean square speed. And for the temperature, we just did the 2. And we got out that the kinetic energy per molecule is 3/2 KB, which is the Boltzmann constant. It's an average, of course. And for a mole, it's 3/2 RT. Okay. That's what I just derived for you, just that you have it here. Now let me ask you a question. No, let me not ask you a question. Let's do some fun first. Have some fun first. Okay. So since we talked about pressures, and we know now how pressure is generated by these force unit area transfer onto containers. So we have a container here. If you could have the light, please. Container, and what Karen did is she filled a little bit of water in that empty soda can, and then she heated it up, that it's steaming, but she doesn't let the steam escape. A little bit escapes. So now the steam is occupying the whole space of the soda can, all right? And so it bangs against the walls, and it's banging from the outside, from the atmospheric pressure. So it's 1 atmosphere. That's when water boils at 1 atmosphere, okay? So it's a perfect balance. That's why this doesn't collapse. Now if she takes this and immediately cools it off very quickly, what do you think would happen? Why would it collapse? Now let's see. Wow, look at that. That was the water that was in here. The can got crushed, okay? So why is that? Because first we had this gas was taking the whole space. Not very dense, but it had to take the whole space, and so it was keeping the counter pressure, 1 atmosphere. And now you condense this gas, and you have a tiny little bit of water, because steam is not very dense. And so you have this tiny little bit of water. So you have all this empty space, which we call essentially a vacuum, and now the outside pressure is much higher than the inside pressure, and the can collapses. Did you understand that? Good. So there is, actually you can do this, you can say, I'm crushing the can without even touching it, okay? So you let your buddy do this, and then maybe you put some green stuff here, like square, and make a bet with them, okay? So you can do this in your frat house, but be careful, or wherever you are, and so you impress your colleagues, the non-scientists, okay? Okay, and that way, so you can also do the same thing here, and this is we will do during our lecture. I have a very large can. That's pretty solid, isn't it? Okay, we'll do the same thing, not we, Karen will set it up that we do the same thing. And so she has a little bit of water in here, and she boils it now till the steam comes, and then she puts a stopper on there, okay? And then we put it here, and it will scare us all. But it will take a time because we don't have an ice bath. It will take a time for it to condense the water. Once it cools off enough, then it condenses and it cannot escape. So let's see what happens there. Okay, so let's put the stopper now. Yeah, that takes a little while. Just don't pay too much attention to it, okay? Because I need to continue my lecture here. So let me ask you a question. Let's see if you understood what I told you so far. You have 1 mole each of bromine gas and hydrogen gas, and you place this in a balloon, okay? You put bromine in there and hydrogen. And you are at the same temperature. Let's do this at room temperature. What are the relative kinetic energies? Bromine, so these are the molar masses of hydrogen and bromine. Bromine has higher kinetic energy than hydrogen. They have the same kinetic energy. Or bromine, the kinetic energy is smaller than the hydrogen kinetic energy. Why don't you think about this and give me your answer? You need to remember what I told you before here. Don't scare me, Karen. So what do we do if there's an earthquake now? What do we do? Make sure that you look up there, duck to get between the seats there, because this stuff will all come down. No panic, that's the most important part, because you kill yourself walking on top of each other. Okay, I'm serious. So Karen has prepared the experiment. Don't put it too close behind me, please. This morning it really scared me because I was forgetting about this. I did forget about it. Okay, let's have a look. That's a Gaussian distribution, that's pretty good. But some of them are wrong, obviously. And so, what did I explain to you when I did this Elmo exercise there? What did I explain to you? What did I say? Didn't I say something like this here? Okay, that was the outcome. Something like this here? No, this here, okay? So why don't you think about this jointly with your neighbors and discuss it and try to give me a more correct answer, or a correcter answer. Okay. So what is it? No, drink the beer, that's good. Yeah? Yeah. It's in the book, it's a little different in the book. Yeah. Water, steam? Yeah, water, just water, steam. That's cooling off now. No, that will take a long time. It caught me totally by surprise. It will catch me by surprise again. Yeah. Okay. Don't forget to click in. Oh, there are about 40 people at home trying to prepare for the test. Yes, there you go. Good. The kinetic energy of a gas or of different gases only depends on the temperature. And you will see why this is when I get a little further in our explanation. So the solution is kinetic energy is right there. 3/2 RT. You see anywhere a mass here? Only here. There's no mass in there. Okay. We have a fixed temperature. R is a constant. 3/2 is a constant. So the kinetic energy of these guys is the same. Depends only on the temperature. And of course, it's the kinetic energy of the temperature 1/2 times the number, that's for mole, Avogadro's number, times the mass and the velocity. So what this means is that larger particles, they have much lower velocity, and smaller particles have much higher velocity at this temperature. But they will have the same kinetic energy at the temperature, gas particles. So this was the answer then. Now, we have this mean square velocity here, or the square mean velocity, and this is 3 kb, we had this here 3 kb, divided by T over M, we can say. We put that M in here. And this is 3 RT over M for 1 mole. And with this, we had, that's no good. You want the velocity, not the bar squared or something? Okay. You want the velocity. How do you take a velocity out of this here? Careful, it's starting. No, it's leaking. Wasn't as powerful as this morning. Yes, still? Yeah. You see that, baby? Can we have the camera, please, on that? You see that? Okay, that's a solid pen. Now, I'm going to try to remove the cork, but it has nothing. It has a vacuum. And so I'm going to pour the water that you see, the water out here. That's what that little water was in there. It was all gas before, and so you can do this with your friends, but be careful, all right? All right? Do not mention that you learned that here, okay? Especially when you're in front of the court, then, okay? So how do I get a square? It says here, it says already, root mean square speed or velocity. So I take the square root of the baby here, and I have something more convenient. So that VRMS, the root mean square velocity or speed, is the square root over this, or the square root over this, or the square root over that. Okay, now I have something I can work with, a root mean square velocity. So actually the dependence is that the root mean square velocity is proportional of the square root of the temperature divided by the mass. There's the mass in there. See that? It better be. And this would be the molar mass. Is that right?